Welcome to The Explainer. Today, we're going to dig into one of the most fundamental ideas in all of machine learning, the super important and sometimes tricky balancing act between bias and variance.
Okay, let's kick things off with a scenario that I'm sure you've run into. You spend all this time training a model, you get its accuracy up to 100% on your data set, and you're thinking, yes, I've nailed it. But then you unleash it on the real world, on new data, and it just falls flat on its face. So what's going on? Well, this isn't a bug. It's actually a feature of a much deeper challenge.
So, here's what we're going to cover in this explainer. We'll start with what we're actually trying to achieve, perfect generalization. Then we'll look at the two big errors that stand in our way. We'll visualize how they trade off against each other, and then get really practical on how to spot and fix the problems. And you're going to want to stick around for the end, because we're going to talk about a wild twist from modern deep learning that's rewriting all the old rules.
Okay, let's dive right in. First things first, what is our ultimate goal? What are we really trying to do when we build any machine learning model?
The whole point, the real magic, is in this one word, generalization. I mean, a model is pretty much useless if it can only tell you things it's already seen, right? The real test is whether it can learn the underlying patterns so well that it can apply that knowledge to totally new situations. That's what we're after. So, to get a little technical for a second, when we train a model, what we're trying to minimize something called empirical risk. That's just a fancy way of saying the error on the data we can see, our training set. It's easy to calculate. But what we really care about, the thing we wish we could measure, is the actual risk. That's the error on all possible data out there in the universe. We can't see it, we can't measure it, but we train our models hoping that by making our measurable error smaller, that other, more important error gets smaller too. But here's the catch. There are two fundamental types of error that are constantly working against us, trying to stop us from achieving that perfect generalization. Let's call them the twin enemies, bias and variance. And I absolutely love this analogy. Think about it. A model with high bias is underfitting. It's like you only skimmed the chapter titles before a big exam. You get the general idea, maybe, but you've missed all the crucial details. On the flip side, a model with high variance is overfitting. It's like you memorize the entire textbook word for word, including the typos. You can ace a quiz on direct quotes, but you can't answer a single question that requires you to actually understand the concepts. So let's break that down. With high bias, or underfitting, your model is just too simple. It fails to capture the underlying patterns, so it performs poorly everywhere, on the data it trained on and on new data. But with high variance, or overfitting, your model is too complex. It doesn't just learn the signal, it actually starts memorizing the random noise in your training data. So it looks like a genius on the training set, but it completely bombs the final exam when it sees new data. So how does this all play out? Well, this constant push and pull between bias and variance gives us one of the most iconic, most important graphs in all of machine learning.
Okay, so take a look at this. As we move from left to right along the bottom, we're making our model more and more complex. Now watch that dashed line, the training error. Of course, it goes down. The more complex the model, the better it gets at memorizing the answers. But now, look at the solid line. That's our tester, the one that really matters.
At first, as the model gets more complex, the tester goes down too. Great, it's learning the real patterns. But then you hit a tipping point. The model starts to overfit, memorizing noise, and that solid line starts to creep back up. Our mission really is to find that perfect balance, that sweet spot right at the very bottom of that U-shaped curve. That's where generalization is at its peak. Okay, so that U-shaped curve is great in theory, but in the real world, you don't get to see the whole perfect picture like that. So how do we know when we've gone too far? Well, for that, we have an amazing diagnostic tool called learning curves. And here is the single biggest red flag you need to watch for. During training, you're keeping an eye on two things: the error on your training data and the error on a separate validation set of data the model has never seen before. If you see your training error going down, 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 but your validation error starts to creep up, Houston, we have a problem. Your model has officially stopped learning and started memorizing. And this is exactly what that red flag looks like in the wild. See that red line for the training loss? It's dropping, looks great. But look at that teal validation line. It's heading in the wrong direction. That gap opening up between them, that is the generalization gap. That is the visual proof of overfitting. Now this, on the other hand, is what we want to see. This is the goal. Look at how the two lines are practically holding hands. They track each other very closely. This tells us the model's performance on new data is right in line with its performance on the training data. This is a model that is generalizing well. So, let's say you've spotted the signs. Your learning curves are diverging. You know your model is overfitting. What can you actually do about it? Well, the good news is we have a whole toolkit to help us find that balance.
We've basically got 4 main tools in our belt. We can add something called regularization, we can use early stopping, which is exactly what it sounds like, we can try to get more data, or we can just make our models simpler to begin with. Let's just double-click on regularization for a second, because it's a really powerful technique. The best way to think about it is like a complexity tax. We add a penalty during training that punishes the model for making itself too complex. It forces the model to only focus on the most important, most generalizable patterns, nudging it back toward that sweet spot on the curve without us having to change the model's architecture.
All right, so for decades, that U-shaped curve was the law of the land in machine learning. It was gospel. But then, modern deep learning, with its absolutely massive models, came along and just threw a giant wrench in the works.
So check this out. Look at the graph on the right. It starts out just like we'd expect. Error goes down, then it hits that peak of overfitting and starts to go up. Classic stuff. But then, something totally wild happens. As we continue to make the model even bigger and more complex, the test error, against all logic, starts to go down again. This phenomenon is called double descent, and it's mind-blowing.
Yeah, you heard that right. It turns out that in this new era of deep learning, once you get into this over-parameterized zone, making a model even bigger can actually make it generalize better. It completely breaks the classic rules we just spent all this time learning. Sometimes the fix for an overfitting problem is, believe it or not, an even bigger model.
And this just leaves us with this huge, fascinating question that researchers are scrambling to answer right now. If a concept as fundamental as the bias-variance trade-off can be turned on its head like this, what other rules are just waiting to be broken? It's a pretty powerful reminder that this field is always, always evolving.